Yeah. Yes. I can't hear you. What? Yes. That's the last one. It's the last one.
When do we gonna start doing sexy?
Start doing what? So this next week I think it's Protista, and then the week after that we have a couple weeks of dissections.
When do we get to
The pigs, that's not till the third quarter. Get to do it again.
Are we hoping that was this quarter?
No, the pigs are third quarter. This quarter it's all invertebrates that we're doing. Worm, clam, sea star. Has to do with the classes you're taking. Okay, good morning, everyone. Okay, let's listen up. So this week for lab, if you have Thursday lab, you're going to print off you only need pages 1 through 4 of the Nanu Stata Lab, and it's in the lab handouts module, so you have to scroll down to find that. For class on Friday, we're going to do our last symbiotic packet, so you need to bring your Isle Royale packet to class, and if you have a computer, bring your computer. I will have the computer cart again. Also, you do have another biomath that's due next Monday, so you might want to start working on that. Okay, and it corresponds to the types of problems that are in Chapter 55. Okay? All right. So any questions about that? All right. So we're going to go ahead and get started. So today we're talking about Chapter 55, the section that was supposed to say omit. So there was the section about logistic and exponential growth. So we're going to talk briefly about that today, but that's what this IO Royale packet is that you're going to be working on Friday. So you're going to actually be manipulating the model, and it's a really good way to understand the math behind the model. So you do want to understand the math behind those models, and I think as you work your way through the packet, that hopefully that's what you're going to get out of it. That's the goal, at least, for you to get that out of it. So today we're going to talk about other topics with regard to population ecology. And so everything that we're learning about applies to human populations as well as animal populations. So the textbook is mostly focusing on animal population, but all of the concepts are the same. Humans are animals, so the concepts are the same as well. So population dynamics is simply patterns and processes of change in populations, but you want to understand what's driving those patterns and processes. A population, so you've seen this definition a few times, so you want to make sure that you know the definition of population. Individuals of a species that interact with one another within a given area at a particular time, and what's really the most important interaction that they're doing? They're interbreeding. They have the ability to interbreed. So you want to add that to your definition of a population. And understanding populations, that whole field is called demography. So there are people who are demographers, who take like the census data and data mine and get lots of interesting patterns and trends out of that. So the whole field of studying populations, whether it's animal populations or human populations, is going to be called demography. Okay? So populations have an age structure, and there are some age structure graphs with regard to human populations. And what you want to be able to do is to look at the shape of a graph and predict what's going to happen with that population. Is it going to grow? Is it going to shrink? Or is it going to be stable? And we'll talk a little bit more about that eventually. So in terms of what ecologists do, so with human population, it's easy because you have the census data, and people fill out questionnaires, and it's all in a database somewhere. If you're an ecologist and you're studying animal populations, usually you're doing some field work. And you're doing field work to count the individuals, determine their ages, calculate the rates at which they're moving, entering the population, leaving the population, reproducing, dying, all of those things. So that's one thing that wildlife ecologists might do. So a lot of times this involves using what's called the mark recapture method. Okay, this is a common way to determine population size for animals. And so you mark, you have to capture them, and then mark them, and then set them free, and then after some period of time you come back and you recapture more of them. And then there's a simple calculation, and it's the maths in the book, and it's one of your biomath problems, to figure out, to estimate the population size. One of my favorite stories from graduate school, I was a TA teaching ecology, and we were going to do this awesome mark recapture experiment with our students. So Jay, who was more experienced TA than I, we drove out to the fish farm and we bought, I don't remember how many hundreds of little tiny fish like this. And then we fin clipped them all to mark them, which was slimy and took a long time, several hours of work. We put them in the pond on campus. So then lab time comes around, and we have and the pond is shallow, like 3 feet deep pond. So we all march down to the pond with our seine, and we're going to do a mark recapture experiment. We did not get one single fish out of that pond. And what we learned is that ducks eat fish. And there was not one fish left in the pond. So that is the sum total of my experience with the mark recapture method. But other people do it successfully. The duck. So you want to know the ones that you want to focus on the ones that are in your biomath. So I'm going to expect that you know how to do mark recapture problems. So that is a formula that you want to know. Yes. Okay? All right. So the age structure is going to show the distribution of individuals across the groups. This is important because some individuals are going to be reproductive and others are not. Okay? And so you need to understand in terms of the capacity to reproduce what percentage of the population is capable of reproduction. And so populations with a large proportion of younger individuals are going to have a greater potential to grow. Okay? So what would you call this phenomenon, this ability to grow? Anyone? Okay, we're going to come back to that. That's fecundity, and that has to do, that's similar to like what we would think of as fertility. It's not the term I'm going for here. I'll come back to that. All right, so this is just showing you what's going on with elephants. And so elephants don't become really reproductive, and their prime reproductive years are between 15 and 25. So, if you have a population of elephants and they're all older than that, you're not going to have very many baby elephants. And if you have a population of elephants and they're all younger than that, you're not going to have many baby elephants being born. So this is just showing you what's going on with the elephants. So what do you see? Do you see any trends from 1970 to 2000 in your graph? Good, okay? So here in the 70s we had lots of baby elephants, and now those have grown up, so they're over here. Okay, and so that's what we mean. You can look at what's going on and predict what's going to happen to your population. Okay? And you can do that with human populations as well. Joycelyn. That's an excellent question, and I don't have the answer for that. I don't know about the source of the graph. Okay? That's a good question. All right, so what some folks do is they'll have one population that they study, and they'll go back multiple times to really understand what's going on. And bird rookeries seem to be a favorite for people to study. So a rookery is an area where the birds come back year after year to reproduce. And so some folks have, they have pretty long data sets on that. They band the adults, they count the eggs, and so on. So, and that helps them understand what's going on with the population dynamics. So life tables can also track fecundity. So this is the number of offspring produced by each female. Okay, so that's the term we use in ecology. For people, we call it fertility. All right, but it's essentially sort of the same thing. Yes, Joycelyn. Number of offspring. Okay. Yes. Okay. So it's defined differently in different places, and I think they switched their definition. So we'll go with what does the ninth one say? Does it say female, female? Yep. Okay. So that's actually a more commonly used definition is the female one. Yep. And it's frustrating when they switch things midstream. So so you're talking about that's one of the numbers that's used for life tables. So this is just giving you an example of what this data set might look like. So these are birds, cactus groundfinches in the Galapagos, and it's just showing you how they're tracking what's going on, and then they're correlating it to ecological events. So why would increased rainfall in the Galapagos increase the fecundity of the birds? Ryan? Great. It increases their food supply. Okay? So here you see there's a drought. So that had a dramatic impact. All right? Okay. So as we've been discussing, life tables can be used to predict future trends. And so for these birds, the mortality was high and then dropped. So you can see what's going on with the population by looking at your data. So it's pretty obvious that the bird fecundity is dependent on their food source, okay, which fluctuates quite a bit with the rainfall. All right. So then you can also use create what are called survivorship curves, and they are correlated with general patterns of life history traits. And there's 3 general patterns, and we are going to use the figures in the 10th edition, which I don't have electronically. I've been complaining to them for 2 weeks now, and I still don't have them electronically. They keep telling me they're fixing it. Someone will be contacting you soon, and I'm like, yeah, but I have class today, not soon. So if you have your book, you want to flip to 1155. And so we have 3. They call them type 1, 2, and 3. So, all right. So let's pay attention here. So we have they've renamed them. They used to just call them type 1, 2, and 3, but they're using these other terms to sort of help you think about what is causing the different shapes of the curves. So physiological survivorship. Most individuals survive to old age. Okay. Ecological survivorship is B here, formerly known as type 2. Individuals face a constant risk of mortality at all ages. So death rate is essentially constant through time. And then here we have maturational survivorship. Most individuals die young. Okay? So that's a good question. Serena said which ones are humans. So over here we have sheep, we have birds, and we have plants. So which one of those is most similar to humans? The sheep. Okay? Well, we're animals. And so we have physiological survivorship. Most individuals survive to old age now, especially with our current medicine. But still, it's still large-bodied animals are usually going to have that type of a curve. So what kind of an animal, so they're showing you some plants down here for this. What kind of animals would have this shape of a curve? Type 3. Insects? Rabbits, probably not rabbits. Would you say frogs? Things that have like lots of eggs and then give them no parental care. So fish that just indiscriminately spawn and the eggs are just kind of left alone. So this kind of a curve is usually associated with lots of parental care. So, humans carrying their little babies around for 2 years, that's a lot of parental care. And this type of a curve is associated with very, very limited parental care. Frogs probably are somewhere in between here. They probably are here. And that, again, so these are idealized curves, right? So no actual population is going to have a curve exactly that shape. And you can see that even from, even the sheep and the bird and they match up fairly well, but not exactly. Okay? So any questions about these survivorship curves? All right. So this is different in this 10th edition. That your book has. It's there, but they're weird shapes. It never made very much sense the way they had it before. Okay. So we have type 1, which we're now calling physiological. Type 2, constant risk of mortality, and type 3. You like these better?
Type 1, type 2, type 3.
Yeah, but so type 1 is physiological, type 2 is ecological, and type 3 is maturational. Because someone decided, Eric, and that's not what they call them. All right, so we just looked at the updated figures in the text. All right, so as we were talking about, I was talking about parental care. So parental care is part of what's called the life history strategy, okay? So that explains how an organism allocates time and energy throughout its life. So they can vary a lot. And the variations can have some impact on how fast the populations grow. So this is part of what we're going to be working on with the packet, the symbiotic packet. But essentially, the intrinsic rate of increase is R, and you have births plus deaths. Okay? So, yes, deaths are going to be negative. So essentially, if birth and death is equal, what would R be? R would be 0. When birth rate equals death rate, R is 0. Okay? That doesn't mean there's no population. A lot of people think when R is 0, the population is shrinking. No, the population is stable. Okay? If it's negative, then it would be shrinking. That's correct. If it's positive, then it's growing. All right. So, in terms of what's going on with your life tables, you have survivorship and fecundity, which are, and we're not going to worry about the calculations for L and M. Okay, you can do that sometime when you take a junior level ecology class. But what you want to know, just conceptually, that age at first reproduction, which is called generation time, is very important. The number of broods per female, so how many times in their life they reproduce. If you're thinking of something, a bird, a brood is, they have a litter or they have a clutch of eggs. They have different words for every organism. But this is, when they're having more than one offspring at a time, you could use that word. And then number of offspring per brood. Okay. So it's really interesting. As I said, all of these concepts apply to human populations as well. So I also teach environmental science, and none of the environmental science textbooks talk about this, generation time. And generation time is really important. So if you think of of humans, if everyone's having if everyone's having 2 kids, but let's say they're all having 2 kids at an average generation time of 15, which in developing countries that's quite common that people have kids when they're 15, versus 30. Everyone's only having 2 kids. So sit down and do some math, figure that out for 90 years. How many people do you have? 90 years. So you have 2 at 15 versus 2 at 30. So figure that out. And you're 90 years total. And everyone's going to live to be 90 years old. Write it on your paper. Or you could use a calculator. Talk to your neighbor. You can, Serena. Let's give everyone another minute, okay? She likes to come up to the board. Let's give everyone one more minute, all right? Don't write anything yet. Control your excitement. Look at her with her marker. I need to see something written down here. So you have 90 years total. We're talking about humans. So we're going to have 2 babies every 15 years. That's one scenario. Or we're going to have 2 babies every 30 years. Starting with, the one person who starts reproducing. Yeah. So generation. So you had 2 babies when you were 15, average age. And so then your babies have babies when they're 15, 2. So you had 2 babies. So how many babies are they going to have? 4 babies. So then how many babies are you going to have? So figure it out. 15 generation time versus 30. I need to see numbers on your paper. Oh, awesome. Very good. Did you talk to Kalani about that? Where you guys got numbers?
60.
Okay. You have numbers? So let's see some numbers. Yes, Mike.
Did we do our math right? Because we didn't want to draw it out and figure it out like that.
2 to the 6, 2 to the 3rd, or 2 to the 12.
Let's see what we get.
Because we got huge difference.
Okay, does everybody have some numbers on their paper? You got numbers. I see numbers. Okay. All right, Serena, go. You're on.
You have to.
Oh, I thought you had it.
I thought I did too, and then we thought about the quantity and didn't realize it didn't.
Oh, this to the how many generations happened in. Okay, so you have 4 generations of kids. Right? So if this is 1, times that by 4. Right?
What do you think?
Yes.
6 generations.
Oh, I didn't even do that.
Okay. Thank you, Serena. All right. So this works. I saw people doing little, counting. That's fine. So you get 2 to the 6th, you get 64. You get 2 to the 3rd, you get 8. So fertility there is only 2. Okay? And everyone's like, oh, if everyone just has 2 kids, we're all going to be fine. Is that true? No. All right? So this is really important, age at first reproduction. And in Asia, the China's only one child policy, they do take that into account. And once people get married, they have to petition to be married, and once they're married, they have to ask for permission to try to have children. And part of the reason is that they're trying to push back that age at first reproduction. All right, so now we have clickers. All right, so here's your first clicker question. Remember that we're answering this silently. If you have clicker 1, you need to set your frequency to BC. Okay, so you're going to answer this quietly, please. We just went over this. So we're expecting over 85 would be nice. 100 would be awesome. Shh, don't pick E. You're not spiting me. I'm not the one getting clicker points. Let's think this through. All right, has everyone clicked? I'm going to close the question. You have 10 more seconds. All right. So the good news is you did very well. All right. And we did just go over that. Okay. So as you're going to see when you do your symbiotic packet, we do have some populations that undergo exponential growth. So all populations have the potential to grow exponentially, and we're going to talk more about why some do and some don't. Okay? So as long as R remains constant, you're going to see exponential growth. Doesn't matter what R is. R can be a low value or a high value, but as long as you keep adding a constant amount, you're going to have exponential growth. So this is a graph that I borrowed from a different textbook because it makes that point quite well. All of these are exponential growth. Okay? Which one has the highest R? The top curve has the highest R. Okay? So this is exponential, and this is logistic, which is also called density dependent. And exponential is also called density independent. So, go ahead.
So when R equals 0, that wouldn't be exponential?
Where on these two graphs does R equal 0?
Why equal that?
This, right here. R is 0 here. That means a stable population. No. Each couple having 2 children forever is exponential growth.
They have to you would have 2.
Look right here. This is exponential growth.
Wait, but if each couple has
Whoops.
children,
They're both exponential growth. As long as you have a constant R, so as long as more babies are being born than are dying, you're going to have exponential growth. Yes?
And R is 0 when density and birth rate are the same?
When R equals 0, birth rate and death rate are the same. Okay? Yes, Serena.
But theoretically, right, if each couple is two people and they have two kids, then it would stay constant.
Only if they die right after their babies are born. They're still alive. They're still alive. Say that louder. You all listen to Chloe here.
If the rate is 15 years for reproduction, then you still have the parents, the grandparents, and the great-grandparents being alive while the babies are being born. So your population is still exponentially growing.
Right. So here you have two being born, and here you have two. Unless you're dying as soon as your kids are born, which is usually, that happens occasionally, but it's not the ideal situation, your population's going to keep growing. Does that make sense? As long, yeah. All right. Okay. So the term is, this is just the change, dn. N is the number of the population, right? And dn dt is your rate of change. And so this can also, so R times N is called the biotic potential. And that's essentially the maximum rate at which the population could reproduce, assuming there was no limiting factors. Well, there's some things are dying, but you're still growing. So you're not limited by food, you're not limited by space, etc. So we do see sometimes early in the population growth. So especially if a population moves and colonizes a new area, they're growing exponentially. There's no limitations. Their growth rate is close to their biotic potential. And the example is on the next slide. Yes, Joycelyn?
So are all populations going to go through the logistic curve?
The question is, are all populations going to go through the logistic curve? So again, let's go back to the curves. These are population models. These are models that occur when you plug numbers into mathematical formulas. Most of the time, you don't see either of these in nature. All right? So even human growth, which is still going up, it's not true exponential growth because the rate of change has changed. The rate of growth has changed through time. Okay? So these are simply population models. Maybe. It depends. You can find populations where the growth looks similar to a logistic curve, but a lot of them are really, really messy. And your book doesn't have lots of data graphs from populations. I'll see if I can find a few more. But some things just fluctuate wildly and don't look anything like those. Like crab populations.
So like some human populations seem to like to have 3 children with another.
Well, but still, that's still one of these. That's just one of these curves. All right. So this is a classic example of exponential growth and then a crash. So why did it crash? There's no more food. So they're reindeer on an island. They didn't have any predators, but eventually they ran out of food. Okay? So a lot of the population dynamics is studied on islands. And the simulation that you're doing on Friday is based on real research on an island, Isle Royale. And it's so why are we using islands to study population? There's no immigration and emigration. Yep. So, not really. On an island, they would all just be one. Yeah. Unless they're like the tiny little butterflies that can only have little patches of flowers. But something like a deer on an island is just one population. All right. So we want to talk about the carrying capacity. So in the logistic growth curve, you see that it approaches this flat line up here. And actually, I'm going to redraw that curve a little bit. Because in the real world, it's not pretty and flat like that. Okay? So again, I said that's a model. in the real world, the population, even if it's stable, it might look something like this. So why is it going up and down like that? It's about the environment. It's about their food or their weather or something. So this is the environment is changing. It could be seasons, but something like deer live longer than one season. Okay? And so this is the carrying capacity, K. And you have to know what K means. Okay? And I don't know why it's a K and not a C. I don't know why. But it's a K. And that's going to be important. And the next part here is important, indefinitely. So it's the number of organisms that can be supported in a habitat for a long period of time, or without environmental damage, without degrading the environment. So that's what the word, you could substitute sustainably there, but it means for a long period of time. Okay? What'd you say? That's an excellent question, and we have a little slide about that. And I have to, yes, that's a good question. All right, so typically we see a logistic curve, which you can call an S-shaped curve. An exponential is called usually what? No, it's not a bell curve. It's called the J. Looks like the letter J. The J-shaped curve, those terms are used for them. And so this is your book, S-shaped curve. Again, this is using math, so in the real world, it would be a lot more messy than that. All right, so we want to talk a little bit about which kinds of organisms have which shapes of curves. And I used this term earlier, density dependent. So when things are approaching their maximum, they start to be limited by things like food availability, or water, or access to mates, or space for their nest, or something that depends on how many there are. So as the population goes up, these density-dependent factors come into play. All right? So I just gave a bunch of examples of density-dependent factors. So what types of factors would be density-independent? So weather, okay, so a drought is density-independent. A big hurricane, what else? Or a really hard freeze might kill all the plants. Disease is density dependent. Why? The more people there are, the more animals, the more opportunity to trade germs around. So disease is always density dependent. If the humans clear-cut the forest, that would be density independent. Everything's dead. Okay? What'd you say? Predators are going to be density dependent. So the more of you there are, the easier it is for them to pick you off. Yeah. Okay, and fire. Fire would be another density independent one. Okay? So you want to make sure you understand the distinction between density dependent and density independent factors. Why is fire density independent? Just if there was a fire in this room and we couldn't get out, everyone in this room is going to die, regardless if there's one person in here, 10 people in here, or 100 people in this room. It's going to kill everybody. It doesn't depend on the density of the people in the room. Yes. I thought your hand was up. No? Okay. So, in terms of ecology, we call them R strategists, because R, they're maximizing that reproductive rate, and K strategists. So, humans are K strategists, even though our population growth is not reflecting that. That's a good question, though. How come human population is still going up? We've increased K. We've increased K with technology, improved food production, increased sanitation, hygiene, antibiotics, vaccines. So we've increased K with technology. Okay? All right. So you have this list in your book about R strategists versus K strategists. So these are going to be the things that tend to reproduce exponentially, the R strategists. So dandelions, houseflies, rabbits, they're going to crash. They're going to run out of food eventually. And then we have K over here, things that live longer, oak trees, polar bears, people. Large mammals, elephants. I just picked one. Okay? So here's what I was talking about earlier. Large parental investment in each offspring. Those tend to be K strategists and have more likely to have logistic type growth. Little to no parental investment in offspring. And then it's also related to your survivorship curve. So our strategists tend to have a type 3 survivorship curve. So that was the one that looked like that. And the K strategists tend to have that survivorship curve. And obviously there's stuff in between, right? Okay, so any questions about what we mean by R strategy and K strategy? And the letters are coming, yes?
Would the R be higher density populations, or is that not high?
No. I mean, they can eventually get to a high density, but then they're going to crash. Or typically what is they go, some of them migrate to a new space. Okay? You can't do this indefinitely because the planet has limited resources.
Would you say a key factor to the difference of them is that like the K strategists kind of reproduce slowly?
Yes.
And then the R strategists just kind of like go for it as they can.
Correct. So the K strategists, reproductive, they invest a lot more in reproduction. They have many fewer offspring. So humans usually have one at a time, sometimes twins. Elephants, one at a time, once in a while twins. As opposed to, yes, so that's definitely true. Okay? So these are the ones that have multiple offspring at one event. Yes. Any other questions? All right. So this kind of summarizes a little bit of what we've been talking about. So species that use abundant resources generally reach higher densities than species using scarce resources. Some things are generalists, some things are specialists, so that's a little bit about what that's referring to. Small body size usually reaches higher densities. So we were talking about the big mammals as K strategists, humans, polar bears, elephants. Okay? Things that have a very complex social organization, like some insects, facilitate high densities. So if you think of human cities, we definitely live in high density situations. All right, so this is about invasive species. This is something called the zebra mussel, because it's striped. And what would you predict, what kind of a growth pattern is an invasive species going to have? Exponential. Oh, it's right here. So much for my question. So they often have exponential growth. And these things are from Europe. They probably got to the U.S. in ballast water. And now they can grow on the prop of the boat, so they're little bivalves, and they actually grow on top of the native bivalves, so they're killing the native bivalves. But they go through the different water features because people have their boat in one lake, and then they take it on a trailer to some other lake, etc. Pretty much that's not true. You can see they came in through the Great Lakes, probably in the ballast water from Europe. All right, so I'm going to skip this meta-population stuff and go to the human population stuff. All right, so the size of the human population is now contributing to, I would say, all of our environmental issues that we have on the planet. We don't focus a lot on environmental issues in this class, but I think it's something that people need to be thinking about. I teach environmental science. We talk about it a lot. I teach a sustainability and systems class. We talk about it there as well. So for thousands of years, Earth's carrying capacity for humans was pretty low. Disease, warfare, lack of food. So the very early human population graph, which they don't have in this book, for a long time was like this, right? It was super low. Okay? And now it's like that. So we've been talking a lot, people, about this, a ZPG, zero population growth, a total fertility rate of 2.1. So this is how many children. This is children. So fertility, this TFR is just children. It's not female-female thing. Okay? And so why is it 2.1? And we're all aware you cannot have 0.1 of a child. Okay, so why is it 2.1?
Because not all of your children or your population are going to reproduce again. You're going to have some that are not reproductively capable. You're going to have some that are going to die or just choose not to reproduce.
Okay. What?
That would lower it. That would lower it, right?
No. So basically, if everyone had 2, so this is to factor in the mortality of the people who don't survive to reproductive age. Yes.
So is that the same pretty much that the average woman has 2 children?
Yes. Yes. That's exactly what it's saying. That the average woman would have 2 children. Okay. All right. So this is talking about how we've increased our carrying capacity. So we've domesticated plants and animals. We had the Green Revolution. We now have clean drinking water. We wash our hands. We use flush toilets. We go to the doctor. We get shots. All that stuff didn't used to happen. So we've increased our carrying capacity with technology. So we want to be able to look at these human age structure graphs to predict future trends. And it's interesting because you can look at some of these graphs and you can see different phenomena in the population. So the baby boom is considered 46 to 64. 75 million babies were born. Then birth rates declined after that, but then there was sort of this baby boom echo as the baby boomers had their babies. All right? So you can see that in the graph. So here's the baby boom, born in the 46 to 64. Okay? And then baby boomers were the dominant age class in 1980. And now we have the children of the baby boomers in green on the graph. And by 2020, the boomers will be as dominant as their parents in terms of the structure of the population. Is it ever going to go back down? What would have to happen for that to occur, Joycelyn? Joycelyn, we're talking to Joycelyn. If people had less than 2 kids, that's the only way it's going to shrink. Okay, so where are we seeing people having less than 2 kids? What? Lots of the European countries. And they're worried because their populations are actually shrinking. France, Italy, Japan. And that brings, what kind of problems does that bring? Nick?
Social security problems. You have lots of older, unworking people being supported by a rather poor and desperate young generation.
Okay, so there's more people getting their pension than you have workers to support the taxes. That's part of it. Also, just elder care. Who's going to physically take care of all those folks? In Japan, they're actually trying to invent robots to take care of people in their homes. They are. They are. They're made quite a bit of. All right. So what would you say about this population structure of Uganda? It's going to do what? Say that louder. It's going to grow rapidly. Okay? Maybe not true exponential growth. So why? It's going to keep growing. Stephen.
Because the young generation are going to get old and then reproduce.
Old enough
to reproduce.
Old enough to have children. Yes. Nick.
Hey, remind me again, Uganda is this place where the dictator there killed several million people or something along those lines, and then they've had, like, starvation and poverty problems.
Their birth rates are huge. The birth rates are still larger than the death rates.
Okay.
Okay, so what do we call this? What do we call this? It has a pyramid shape. Okay, so when you're looking at the shape of the graph, if you see a pyramid, your brain should say, oh, that population's going to keep growing. Okay, so the pyramid shape is what you're looking for, but there is a term for it, and it was in the book, I'm pretty sure. It was in the 9th edition. I have to double check the 10th. It's called population momentum. Okay? That's an important term for people to know. Because everyone just thinks that this is the magic pill, 2.1. Is that the magic pill? No, it's not. Okay? Which we saw over here again. Okay? So it's a lot more complicated than we understand. So some of the European countries are experiencing population declines. So you're going to see this is more narrow than what's going on here. So Italy, France, this is Germany, Japan. The Scandinavian countries are a little more stable. But some countries are actually subsidizing. They're paying people to have more kids because they're concerned about their economy. All right. So you also, in the 10th edition, you also have this figure, which is on 1165. And it's showing you just since 1950. So how many of you know people who were alive in 1950? For most of you, that's probably your grandparents. But look, we went from 2.5 billion to 7 billion people on the planet in the last 60 years. Wow. Okay? So that's significant. This is now, we passed 7 billion in about 2012. So there's a few different estimates. Okay, so this, you want to know this. This is a fact, but you all need to know there are 7 billion with a B people on the planet. Okay? There's 7 billion people on the planet. Here, this is one projection, and there's other projections. We're going to talk about that in a minute. There's some, it depends. It's a projection, right? What's our current carrying capacity? Do we know the current carrying capacity? No, we don't know. Okay? Hang on. So what did we say was the definition of carrying capacity? Without destroying the environment. Do we have evidence that there are places on the planet that we're destroying the environment? Yes. Okay, so a lot of folks, there are definitely people arguing that we're already past our carrying capacity. So we're at 7 billion, if we're past the carrying capacity, what's going to happen? All right, so climate change is part of how we're exceeding our carrying capacity. Here, these are the, listen up, you guys, this one's not in your book. These are different projections. So you can go to, like, the United Nations has some great websites, and these projections are from their numbers. So you can, in your book it had 9.4 billion. Yeah, so that's kind of the medium projection. So this is low, this is medium, this is high. This is if fertility doesn't decline, which is even higher than high. Okay? Globally, fertility is declining. It has been for decades, but we're still growing. Yes.
Does fertility in humans declining have anything to do with genetic foods or genetically modified?
Probably not. Probably not. Okay, so here, this is telling you medium. So medium is this magic thing, 2.1. Okay, so we're still going to keep growing. Low is 1.7, TFR of 1.7, and high is 2.7. And I couldn't find current. Obviously, it's higher than 2.7. Wow. I'm hoping you're saying wow. That's the point. Wow. Okay? So I think that we're out of time. So, I do have the test. So if the Tuesday people got their test back, Thursday people, I will give you your exam.